Our number journey often starts simply. We count objects, we learn about whole numbers, then come fractions, negatives, and real numbers. These numbers fill a line. Mathematicians, however, seek more. They explore new numerical landscapes. Complex numbers were a significant step. They added a new dimension using the imaginary unit I. This I is the square root of -1. It allowed solutions to previously unsolvable equations. This expansion of number systems is a recurring theme in mathematics. It opens doors to understanding richer structures. William Rowan Hamilton had a flash of insight. He was walking by a bridge in Dublin. He sought numbers that could describe three-dimensional rotations. Complex numbers worked for 2 dimensions. For 3 dimensions he needed something more. He discovered quaternions. These numbers have 4 parts. 1 real part and 3 imaginary parts, I, J, and K. These imaginary units have special rules. For instance, I squared equals J squared equals K squared, all equal to -1. This was a new kind of algebra. Quaternions live in a 4-dimensional space. Their most startling property is non-commutativity. This means the order of multiplication matters. For normal numbers, 2 times 3 is 3 times 2. For quaternions, I times J equals K. But J times I equals -K. This was a radical departure. It challenged the fundamental rules of arithmetic. Yet, this very property makes them powerful. They perfectly describe rotations and orientations in 3 dimensions. This is vital for computer graphics, robotics, and physics. Soon after quaternions, a friend of Hamilton, John T. Graves, pushed further. He wondered about an 8-dimensional algebra. His discovery, independently found by Arthur Cayley, was the octonions. Octonions have 1 real part and 7 imaginary units. They extend the ideas of quaternions, but they introduce an even stranger property. Octonions are non-associative. This means A times B times C is not always a times B times C. Grouping matters. This makes octonion arithmetic incredibly complex. Yet, these exotic numbers hint at deeper connections. Some physicists believe they might play a role in understanding fundamental particles and forces. Prime numbers are mathematics' oldest mystery. They are the atoms of arithmetic, whole numbers greater than 1, divisible only by themselves in 1. Their distribution seems random, yet patterns emerge. Mathematicians have long sought a deeper order. Could these higher dimensional algebras offer new perspectives? Imagine a prime dimension, a space where primes are not just points on a line. Perhaps their properties unfold in more complex ways. Quaternions and octonions could provide the language for this space. One intriguing concept is asymptotic curl. Think of primes spread out, not just in a line, but in a higher dimensional field. Asymptotic curl describes how their density might twist or spiral. This is on a grand scale. It is like watching a cosmic galaxy of primes. Are there preferred directions or flows in their distribution? Do primes tend to cluster or align in specific ways when viewed through a quaternionic lens? This concept tries to capture such large-scale geometric features. It hints at underlying currents in the seemingly chaotic sea of primes. Orthogonality is another key idea from these algebras. In geometry, orthogonal means perpendicular. It implies independence. In quaternionic or octonionic spaces, components can be orthogonal. They represent distinct, non-interfering aspects. How might this apply to primes? Perhaps different characteristics of primes could be orthogonal. For example, a prime's size might be 1 dimension. Its relationship to nearby primes another. Specific forms like Mersenne primes could occupy unique orthogonal states. This could help classify primes in new ways. The significance of such orthogonality is profound. It could reveal hidden structures within the set of all primes. If certain prime properties are truly orthogonal, they behave independently, yet they contribute to the overall character of the prime. This is like having different instruments in an orchestra. Each plays its own part. Together, they create a complex symphony. Finding these orthogonal bases in the prime dimension could be a major breakthrough. It would offer a new coordinate system to map the prime landscape. It could simplify complex relationships. Could primes possess fixed angular states? This is a speculative but exciting idea. Quaternions are masters of rotation. They describe orientations in 3-dimensional space. Imagine if each prime or classes of primes had an intrinsic orientation within this prime dimension. This orientation would be represented by a quaternion. It would be a fixed property like its value. This moves beyond primes as mere scalars. It gives them a directional geometric character. Their interactions might then depend on these angular states. Rotational matrices can be derived from quaternions. These matrices transform vectors in space. We could use them to model prime behaviors. A prime's fixed angular state could define a specific rotation. When primes interact in this model, their rotational matrices combine. This is not simple multiplication. It follows the non-commutative rules of quaternions. The outcome of such an interaction would depend on the order and on the initial angular states of the primes involved. This framework could model dynamic properties of prime sequences. Let's consider examples of quaternionic prime interactions. Suppose two primes, P1 and P2, are each represented by a quaternion. Their product or interaction, P1 times P2, would yield a new quaternion. Its components would reflect the combined properties. Because of non-commutativity, P1 times P2 would differ from P2 times P1. This could model situations where the order of influence matters. For instance, how a prime influences the probability of another prime appearing nearby. The resulting quaternion might encode this directional influence. Extending this to octonions makes things even more intricate. Octonionic algebra is non-associative. Consider an interaction involving three primes, P1, P2, and P3. The result of P1 times P2 times P3 might be different from P1 times P2 times P3. The way primes group or cluster could be modeled by this. Imagine small clusters of primes forming. The properties of the cluster depend on how its members came together. This non-associativity could capture subtle, context-dependent relationships. It could describe non-linear clustering phenomena observed in prime distributions. It suggests a very rich, complex dynamic. Applying these algebras could revolutionize our understanding of prime alignments. Current methods often look at primes on a number line, or perhaps in simple two-dimensional plots. Quaternions and octonions offer four-dimensional and eight-dimensional frameworks. These higher dimensions might reveal symmetries and patterns invisible otherwise. It is like finding the right perspective to see a hidden message. Prime constellations or peculiar gaps might find natural explanations. We could uncover a geometric order underlying their arithmetic nature. This could lead to new theorems about prime distribution. The connections to quantum theories are tantalizing. Non-commutativity is a cornerstone of quantum mechanics. Position and momentum operators do not commute. This leads to uncertainty principles. If primes exhibit non-commutative behavior via quaternions, does it hint at a quantum-like nature? Octonions are even more exotic. They appear in some formulations of M-theory and string theory. These theories try to unify all fundamental forces. Could the mathematics of primes and the mathematics of the universe share these deep algebraic structures? It is a profound question. The implications may extend beyond pure mathematics and physics. Prime numbers are fundamental to cryptography. Secure communication relies on the difficulty of factoring large numbers. A deeper understanding of prime structure could, in the long term, impact this field. It might lead to new cryptographic methods, or it could reveal vulnerabilities in current ones. Complex systems in biology or finance also show intricate patterns. The mathematical tools developed for primes might find applications there. Understanding nonlinear interactions is key in many areas. Ultimately, exploring primes with quaternions and octonions is a journey into the unknown. It is highly speculative, yet it is driven by the mathematical quest for unity and understanding. The primes have always been a source of deep puzzles. These advanced algebras offer new languages. They provide new tools to probe these ancient mysteries. Perhaps the music of the primes, as Riemann envisioned it, has even more complex and beautiful harmonies. Harmonies that resonate in higher dimensions. Harmonies waiting to be discovered by these algebraic explorers.